On behalf of the School of Arts and Sciences and Penn Engineering, I am very pleased to welcome you to the 7th Annual Thomas and Yvonne Williams Lecture for the Advancement of Logic and Philosophy. We are most grateful for the generosity and vision that Tom and Yvonne have shown in establishing the fund that supports this series of lectures and that makes possible other educational activities at the university and at upper schools in our region. It was a great pleasure to work with Tom when I first arrived at Penn and to watch him develop through the study of logic and philosophy that clarity of mind which he has so successfully brought to bear in the sphere of practical affairs, and that sustains his ongoing passion for the life of the mind. And it remains a great pleasure to work with him now on a range of activities that will advance a general appreciation of the power of reason to clarify problems both practical and theoretical. I am delighted to introduce this year's Williams lecturer, Peter Freyd. Peter is an internationally renowned expert on category theory and its applications in computer science. He pioneered the development of topos theory and its use in articulating precise semantics for programming languages. In 2010, he was awarded the Lick's Test of Time Award for his 1990 paper, Recursive Types Reduced to Inductive Types. Peter is professor of mathematics and of computer and information science here at Penn. He has played a leading role in the university's logic and computation group since its inception. His deep insights and fierce intellectual honesty have inspired the group for many years. Please join me in warmly welcoming Peter Freyd, who will speak to us about an anti-philosophy of mathematics.
I received an email, which is what I want to show you. The author refused to let me use his name. I will be talking about an anti-philosophy of mathematics, but that's just one tiny thing compared with other things which are more in the realm of philosophy of mathematics. And you will also hear that I have some things to say about anti-philosophies, maybe of some other subjects. But I have to say this list of people, the first four names are from Brown University. By the way, there are names that are there that shouldn't be, and some that should be but aren't, and there are names that are there that shouldn't be. And that's the very first one, Kurt Dukas. Is that name still a name to contend with in the world of philosophy? He was well known in his day, and I'm afraid that when I knew him, he was the grand old man of the Brown philosophy department, meaning he was about a year younger than I am now. And his subject, I'm afraid, was paranormal phenomena. And it wasn't until, and I never sat at his feet, it wasn't until years later, like maybe 10 years ago, that I find out that this is the founder of the Journal of Symbolic Logic, the first president of the Association of Symbolic Logic. There was no trace of that when I knew him. The next three are people from whom I took graduate courses in philosophy at Brown. Wesley Salmon has gone, he was then something of a logician. He's progressed beyond that since. Stephen Kerner from England was there for just a year. It was essentially the beginning of his interest in the philosophy of mathematics. There were three, as I say, when I said graduate courses, they were in fact all seminars. And Roderick Chisholm was the important one. He did have a strong influence on me over the years. I do have a copy of this. Oh, I've got one right here. Carl Hempel doesn't belong there. This now starts with a few names from Princeton. I had very little contact with him. Alonzo Church. The mystery to me about Alonzo Church is why he insisted I wasn't able to come to a fest for his retirement. And I finally received word years later. I did listen to him occasionally, but I certainly never sat at his feet. Years later, I found out from an organizer that he not only once made me, I made him laugh out loud, I did it twice. And he thought that this was a remarkable achievement, and therefore I should. Kurt Gödel, I never really had, but maybe the time will come. In fact, a number of the names now, mysteriously enough, even though I first met them or talked to them somewhere else, reemerge as important figures. I have two microphones here at the moment. Here with connection with Penn. Now there's a long story. When I received this email and looked at it, I realized that a whole bunch of stories to tell you about Penn in philosophy in the 1960s, and nobody's left except me, and to some good extent, Ervin, who was attending about as many philosophy colloquia as I was, meaning all of them actually. Ervin has been at Penn since 1954, and was a member of the faculty since 61. I came in 62. If this were a year earlier, I could say that Jim Ross is part of that crowd. He also came in 62, and we attended the same graduate seminars. I should make that inclusion the right way. He attended the same graduate seminars that I did at Brown. Ernest Nagel I talked to a bit at Columbia, but again, he comes up in connection with Penn. Now we come to the Penn part. Here represented actually by just a few names. So let me go back to 1962. It was a seller's market in those days, meaning that when you went to a math meeting, people started offering you jobs before they even knew your name. That's literally the correct. And I agreed to come down to Penn as a favor to a young person in the faculty whom I knew. And they did a sales job on me. Penn was in a state of receivership. That's not my word. That is my word, sorry, it's not theirs. There was a receivership committee chaired, if I'm pretty sure, by Britt Chance. Where's Murray? Is that right, Murray? Was Britt Chance the chair of the receivership committee for mathematics? You think about it. There was only one mathematician on the committee, and they wanted to rebuild mathematics at Penn. And they seemed to have what they considered a lot of money, and they insisted that I could build a department at Penn. I was 26 years old at that point. So actually, they talked me into coming. Now, Penn's status in the Ivy League of those days was quite iffy. The phrase you would see in a number of publications was that Penn was déclassé. How much of this is known anymore? Penn started, of course, as a football league, hence the word league. Penn had moved, the Ivy League started as a football league. Penn had moved away from it. It was often considered the 11th Big Ten. The 11th Big Ten finally did come into formal existence, and it turned out to be Penn State, but that's a different matter. And somewhere along the line, just a few years earlier, fortunately for all of us here, the university decided to renew its its Ivy League football league status, which meant that they had to go along with all those rules. And this has clearly had a tremendously good effect. And it also gave Penn something of an advantage in hiring people. So I did come. Now let's go back a bit. What was Penn known for in those days? One knew that it had a good medical division. Beyond that, it had 4 departments, just 4. Anthropology, archaeology, they had been the best departments essentially in their subject from essentially the beginning. Linguistics, and Nelson Goodman. That was it. I mean, meaning the philosophy department. I arrive here, and guess what? Nelson Goodman isn't here. He was on leave. He was in Cambridge, Massachusetts. It was clear that he had some very attractive offers, at least one. I'm not sure how many he actually had. A chairman had been hired away from the University of Buffalo. Marvin Farber. He should not be in this list. I certainly never sat at his feet. You'll hear quite the opposite in a moment. Well, you didn't sit at my feet, that's for sure. As it was with Ducasse, I was flabbergasted to learn later some aspects about Marvin Farber, such as the fact that he was, quote, and I'm quoting directly from the literature, a protege of Zermelo. I learned that within the last week. This is absolutely flabbergasting to me. At those days, the university was run from the faculty club bar, starting about 5 o'clock. And the provost would arrive, fantastically good provost, David Goddard. And you could do a lot of business if you were willing to go to the faculty club bar at that hour. I found myself there one evening, sitting at a table with the provost on one side, the dean of what they then called the dean of the college on the other side, Otto Springer. His subject was German. And the dean told the provost that, much to his surprise, the department didn't want to keep Nelson Goodman. I didn't say a word. I thought I'd better check. I'd been going to colloquy. I knew a good part of the department at that point. The next morning at about 8:30 in the morning in the provost's office, outer office, there was a crowd of us. I was the one non-member of the department. Marvin Farber had lied. It was a straight out and out lie. Why he thought he could get by with it is beyond my comprehension. We went into the provost's office for some reason, I guess precisely because I was the one non-member of the department. People turned to me and I said, good ploy, I said, we're here to recommend a university professorship for Nelson Goodman. That worked. He came back the next year, but only for 1 year. He eventually did go back to Cambridge. But as I said, I was attending all the colloquy. I gave a number of colloquy in those years. And a receivership committee, again, not their word, my word, was set up under the chairmanship of the dean of the graduate school, Roy Nichols, historian. The very first meeting I was there, there was one philosopher, Joseph Clark, Francis Clark, sorry, if that means anything to anybody, who never said a word in the entire history of that committee. On the opening day of the committee, the chairman said, of course, we're going to go very slowly here. We're not going to make any rapid decisions. An hour later, the committee unanimously voted that we should make every effort to get Hao Wang to come to Penn. I was aware that Wang was movable for some family or personal reason from Harvard, and he damn near came, by the way. Rockefeller University got him from us at the end. But then I was hiring, at the age of 26, I was hiring people for temporary, yes, I was hiring young people, actually, and the next name, Stanley Tenenbaum, is a part of that list. He was sane at that point. Next few years, we did see Paul Bernays, and now an interesting sequence of people who aren't on this list somehow were around here at Penn. One was John Myhill. He was being kept alive, and that's literally the case, not by the philosophy department, but the computer scientists. The computer science department didn't officially exist until 1972, but there was a graduate group in computer science. Mario Bunga was here. Now, I didn't have anything to do with that, but he was here. And at least from that, if I didn't sit at his feet, I at least got my first PhD student, namely his wife. Well, anyway, no, it's not a hoax, but it's not the way it appears. I do want to talk about a possible philosophy for mathematics. And so now I get a bit more serious. So by the way, just before I leave it, as I said, as far as I can tell, only one person left who was actually part of that receivership committee and all that sort of thing. Well, that I know for sure. And it's a strange, weird little piece of history that you had a philosophy department, which a few years earlier had an international renown, in which a 26-year-old, 2 years out of his own PhD, was hiring people for the philosophy department. Well, Jim Ross became chairman, and the rest is history. By the way, the first person presently here to come after that was Charles Kahn. That was 1964. Yes, so as any mathematician knows, if you're going to talk about something, you need a definition. As just about every philosopher knows, if you're lucky, you'll end up with definitions, not start out with them. And that, of course, is the case with mathematics. And there's the central question, how in hell do you define mathematics? And I want to start there. There's an informal reason for wanting something like a definition, as you all know, that you try to communicate to people who aren't mathematicians what it is that mathematicians do. And so I wouldn't consider this to be anything serious, but it was just effort of communication. If I'm in the right mood, I found over the years, if you want an interesting time, casually say that, oh, you invent mathematics, and watch the reaction. But if you're not in the mood for that you have to be in a special mood for. You want to communicate that mathematics is a subject matter, that it's not just a body of techniques. So one wants to distinguish between mathematics on one hand and the mathematical on the other hand, albeit mathematics presumably is one of the mathematical subjects. And in that process, I found myself saying like things, it is a subject matter. I would use the phrase, it is about something. 1969, the summertime, in the city of Brunswick, Maine. I was saying that to a group of people. And another mathematician, now dead, named John Isbell, interrupted me and said, I don't know if it's about something, but I do know that it's not arbitrary. And he instantly stopped me. Now, John didn't want to go so far as to say that you could define that mathematics. You could use that to define mathematics. I'm not sure if you can, as you'll hear that we have to keep poking the definition to get something that actually works. But the way I first wanted to phrase it was, if there were a word in English that stood as the opposite of arbitrary, I could use that word to say what mathematics was, what the subject matter of mathematics was. And in fact, English may have that word. The word may be mathematics. And there's a lot that stems from this. I mean, you can proceed. In fact, in the next half hour or so, I will try to give some examples of answering some typical questions, such as, for instance, the unreasonable effectiveness of mathematics, to use Wigner's wonderful title of his paper. But now let me jump right now. This isn't all I have to say about it, but where this notion of anti-philosophy comes from. There's the possibility, if that's the case, if mathematics is that which is least arbitrary, then when you ask the question, what is the meaning of a sentence in mathematics, you're asking for something, if you think about it, necessarily more arbitrary than mathematics, and therefore may not be a well-posed question. Now, there are many anti-philosophies in this sense of the word, meaning, in fact, I've been predicting for years that somebody is going to come along and prove a Gödel-like theorem to the effect that any language sufficiently rich, that to be defined, necessarily allows you to ask questions which don't have any conceivable answer, but sound as if they should. We're used to that in a number of special cases. We're used, for instance, in mathematics, except this is a very applied mathematics, to know that to ask what frequencies are present in a signal at a given instant, it just doesn't make sense. You can't, the definition of frequency or how you would measure it is such that you can't ask that question without specifying a non-zero interval. And this indeterminacy between time and frequency, of course, can be used to explain just about all the physical indeterminacies. Or some other ones, for instance, the curvature of space. To ask, what's the curvature of space? You can't expect to get an answer unless you start talking about how you're going to use physics to measure it. So you need to know the physics you're assuming in order to answer the question, what's the curvature of space, meaning real space, the space we live in. And there are a whole bunch of things like that that we're already used to. There's one which I like to throw at mathematicians as an example, but I warn you, people can get very upset at this one. If somebody takes set theory as a serious foundational language for mathematics, I can pose to him, because of its untyped nature, the question, are there any simple groups that appear as zeros of the zeta function? I've seen people get very angry at this. I've seen people forget why I mentioned it. Say, I didn't really ask it, I only mentioned it. I've had people come back to me 2 weeks later swearing at me for bringing up such an absurd question. Okay, that's transparently absurd. Notice, by the way, you have no way of answering it at all, even if you took it for the moment seriously, until you specify what definition of group you have in mind and what definition of complex number. And then after somebody specifies them, I've challenged people, now prove to me that there aren't any simple groups that he's got. Look, as I say, there are a lot of these. And one of them may be, one of these questions I'm suggesting may be, what is the meaning of a mathematical sentence? Well, let me come back to that. But that's the only thing anti-philosophy means there. The idea that the non-arbitrariness of mathematics might be its defining characteristic, maybe, I'm not sure about defining characteristic, but it's certainly an important aspect of it, of course, has been anticipated any number of times. Indeed, the most famous definition of mathematics that exists is right here. See if I can scale it down. I can't scale it down. Can I move it? There we go, let's see. I seem not to be able to scale that down, or now it's too small. Leave it like this, okay. You notice that, except it's not there. There must have been an easier way of doing this. Anyway, it's mathematics is a science which draws necessary conclusions. Why is it in handwriting? Okay, another little story about pen from the 60s. In fact, this is 1962. The graduate students in the math department came to me with this funny-looking book. It was about this size, very thin. And each page looked like this, except for the title page. The damn thing was hand lithographed, it turns out, from a single lithograph stone that they kept cleaning for the next 100 copies. There are only 100 editions. This is the first publication, official publication, of the National Academy of Sciences that hadn't been founded that much earlier. It was finally, I think, appeared around 1872. The lecture was 1870. And it is the book and title. The title is there visible here. Linear Associative Algebra. Let me just talk about it for a moment. It doesn't really have anything to do with the philosophy, but it's fascinating that this book was just stacked appeared in the stacks at the Penn Library, one floor down. I actually kept it in my house for a year, enjoyed showing it to people, and wondering if they'd ever noticed that it was missing. They never did. I took it to the rare books side of the library, where it still resides, I'm pretty sure. As far as I could tell, in the last week, I can find no evidence that any copy of it has ever been sold, amazingly. Apparently, at least there isn't any record of any, so nobody knows the value of it. Benjamin Peirce's son, I haven't given the name yet, have I? I can't, unfortunately, I have no control over here. There are other pages I could look at, but I can't at the moment. Benjamin Peirce. So since his name isn't here, let me at least write it. And indeed, this is about the end of it. This was the only thing I wanted this for. So why don't we kill this and get rid of the screens. No, it didn't work. Turn off left projector. Turn off right projector. Good. And let's take these down. Take them up. I used to think I only had left-right confusion. I am not misspelling it. I once had 2 signed recommendations on my desk, both from Harvard Peirce instructors, both of whom thought that they were Peirce instructors. Next time I saw Barry Mazur, in fact, he was at, I said, here, I've got to show you these. He said, I don't want to see, I've given up. You can't do it. The name is spelled that way, and it is Peirce. The book which I was just showing is, by the way, for the mathematicians in the crowd, is the first known instance of such words as idempotent, nilpotent. The person's decomposition is there. Of course, he doesn't give it a name. It is commonly said to be the first book in mathematics ever published in America. His son, far better known than Benjamin, Charles Saunders, got it reprinted about 10 years later after his father had died, and then in fact put it into a book form, made a number of changes where it did gain some frequency, particularly in Europe. I've even seen the statement that it is the first work in science to come out of the United States, which meant that whoever wrote that hadn't heard of Benjamin Franklin, but that's a different issue. There was a wonderful period when I could go around, and then the question became too well known. And I really enjoyed doing this with electrical engineers in this building. And I'd say, who's the greatest electrical engineer ever associated with Penn? And they wouldn't know. And of course, it was the inventor of the lightning rod, and the words positive and negative, and conductance, and resistance, and all those words. Sorry, go on here. Where was I? Oh, just how the first book came in. But where was I? I've lost track of what I was saying. There's his name, at least. That book, that sentence rather, I had no idea it was in that book. That sentence, let me say a little bit more about this. Sorry about that book. It's fascinating because Benjamin Peirce did have a lot to say about the philosophy of mathematics, and his book is a counterexample to almost everything he said. He amazingly was dedicated to applied mathematics. This book, The Linear Associative Algebra, I should tell you, classified all associative algebras over the reals up to dimension 6. It created a subject, well, not quite the subject, it may be in that generality it created it. And it's the only thing that he did the only important thing that he did that was actually in pure mathematics as opposed to applied mathematics. Quite remarkable how that work, which has his most famous single statement about the nature of mathematics, was in fact a counterexample to his philosophy of mathematics. Now, there's a word in that line which I want to take quite seriously. Let me pause for a moment. Grattan Guinness has published a very nice history of the work. He got hold of some original manuscripts and whatnot. And the word necessary comes in quite late. For a while, it was mathematics is the subject which draws conclusions, tried inferences, a few other things, and apparently from some correspondence, he was troubled by the fact that the same thing could be said about law. So he decided to put the word necessary in there. Word necessary is not the same as arbitrary, and in fact, of course, the words are different. But in fact, it's easy to find counterexamples in each direction. But it's similar. It's in that nature. But the more important word, from my point of view, is the word conclusions. Because without theorems, there's no mathematics. And so that has to be added to the mix. It's not enough to say you're non-arbitrary. You also have to have theorems. So let me give an outrageous example. If you want a lot of theorems, the other way, if you want a lot of non-arbitrariness, just start with an empty theory, right? And then you're totally non-arbitrary. You don't have to worry about anything. So clearly you have to have some criterion for having theorems. Couple that in, the existence of theorems and the non-arbitrariness, I don't think there's a huge mystery about the unreasonable effectiveness of mathematics. First of all, it's worth noting that very small part of mathematics, I think, ever finds an application. See, there's a problem of perception here. There's all sorts of areas of mathematics we've now totally forgotten about because they've stopped doing theorems and they never found an application. So one which I like to take as an example is finite geometry, finite projective planes, for instance. I don't think anybody has ever talked about a conceivable application for that subject. With one exception, the last theorem was proven probably well over 100 years ago. The big question is, why is it that all finite projective planes have prime power order? That's a matter of observation. Nobody's found a counterexample. Since I am talking about it, let me say the one exception was that about 20 years ago, they did prove that there are no projective planes of order 10. 6 is easy, comparatively. 10 took one hell of a lot of work, tremendous amount of computer time. I have a personal story. I was having breakfast at John Thompson's place it was a Sunday morning in Cambridge when, what's his first name? He pronounces it McCoy, spells it McKay. John McCoy came with the wonderful news that because of a lot of work of John Thompson, they had reduced the question down to something that wouldn't cost more in computer time than it had cost to get a man on the moon. And so therefore one knows that we could do it, right? In the next 10 years or so, actually it was about 8 years, the improvement of computers and the improvement of the method for search got down so that in fact they got an answer. 12 is still open. So you know, it's a subject with essentially no theorems left. And the other hand has consumed tremendous amount of time on the part of mathematicians over the ages, including what was almost certainly the history's greatest group theorist, John Thomson. And in fact, he will come in occasionally in the morning, he used to, and come in and said, I was thinking about the problem again. And the problem meant projective geometry, finite projective geometry. If you don't know what finite projective geometry is, doesn't matter, it has absolutely no relevance to what I've just been saying, since it's never found an application. But a certain minority of mathematics does find applications, and it looks remarkable. If you look at Wigner's paper, he points to these branches of mathematics that had nothing to do with physics in the beginning, nothing to do with the real world, and yet they became important in physics. But they were non-arbitrary, number one. Number two, they had theorems. Now, the importance of theorems, I think, should be clear, but let's pause for a moment. The group theory has had an incredible number of applications. And it's a subject which has just incredible theorems, right? I mean, I think it strikes everybody. Amazing, starting with so little, how much you get. Well, group theory is officially a part of semigroup theory. There is something called semigroup theory. It has very few theorems that aren't about groups. And yet the world has far more semigroups than groups. They're all over the place. And it's never become anything close to an applied subject. Now, peculiarly enough, if you even further generalize it, and it's possible to view categories as a generalization of semigroups, then amazingly it finds applications. Now, having lived through this, having lived in a subject which was criticized for being so far abstract that it couldn't possibly have anything to do with anything, and then watching two different subjects, quite disparate, physics, theoretical physics on one hand and computer science on the other, finding applications of it. But of course it was the theorems that got applied, not just the language. It was the fact that there were theorems and in each subject that were looked at after the fact as if they were tailor-made for the application. So I don't consider that a huge mystery, is what I'm saying. But notice now that I've slipped in something here. Notice that Peirce's word was conclusions. My word is theorems. What's the difference? There is certainly a difference. There are all sorts of conclusions that none of us would call theorems. And so what's the difference? Well, interest. So there's an aesthetic issue involved here. Does it all come down to aesthetics? I mean, what makes a theorem interesting? Why do we tend to agree, which there are a remarkable amount of agreement compared with other subjects on what's interesting and what isn't. There could well be a philosophy of the aesthetics of mathematics. I'm not aware of it. People are making aesthetic judgments all the time. It's constantly being made while you're doing mathematics, while you're learning mathematics. It is different. Making the aesthetic judgment strikes me as something different from studying the philosophy of such judgments. That seems to be true everywhere you use the word aesthetics. Let me pause just for a moment here, by the way, I intended to say this earlier, since the notion of aesthetics has arisen. That same line that John Isbell used, I don't know about that, but it isn't arbitrary, can be used other places besides mathematics, you know, and I've found it useful. So right on this campus a few years ago, I discovered that architects are used to explaining what they feel about aesthetics with the line that aesthetics are innate. I said, I don't know if they're innate. I just quoted Isabel, just changed the subject. I don't know if aesthetics are innate, but I do know they're non-arbitrary. And that's, of course, what they meant. There's no need for them to be innate. They might be, who knows? It's irrelevant. So let me, the notion of arbitrariness, of course, now I haven't paused over it. I do need some special properties on this. First of all, notice it's not dichotomous. Some things are more arbitrary than others. Chess is more arbitrary than Go. I found people who don't see that right away. But think of the opening position in chess. A whole bunch of arbitrary decisions were made in order to invent that opening position. You could ask, why are the bishops closer to the center of the board than the knights? I don't think anybody ever, if there's any evidence that anybody ever experimented with the other possible opening positions, I've not found it. And notice an experiment would be almost unbelievably difficult, because you'd have to wait a few hundred years to find out whether those opening positions led to interesting games, right? Go seems to be almost entirely, there's one clearly arbitrary aspect of it, and that's the size of the board, 19 by 19. There are some others, by the way, just to be sure here. There are different ways of scoring. They almost always agree on who the winner is, but there are different ways. There are different ways of resolving the possibility of periodicities. You might have a game that goes around in circles, and so you want something to prevent that. And there are some different choices. But interesting, in my looking at the literature on Go, people who are serious about Go seem to take those as variations of the game of Go. There are standard things, standard ways in which international championships are decided but whatnot, but they are viewed as arbitrary. So here's a case, notice that the notion of arbitrariness is you enhance the non-arbitrariness by generalizing. But please keep in mind there are plenty of cases where it goes just the other way. Clearly, the single most non-arbitrary thing we study is the natural numbers. And that's one, it's categorical in the old-fashioned sense of the word. There aren't any variations of what natural numbers means in the sense of number theory without an adjective in front of the word number. So one has to tinker a bit with the notion of arbitrariness to begin to make this work. There is a thought experiment. Every so often I do meet somebody who I find resistant to this notion of what do I mean by arbitrary. Well, there's a clear thought experiment which I know that I use. I'm not sure other people want to use it. But the thought experiment I'm talking about is, what do you expect when you talk to another intelligent species in another solar system? You pretty much expect them to have a game of chess. But it won't be our game of chess, right? I mean, that sounds highly improbable that they would. In fact, I think if we had this chess with the same opening position, we would immediately have evidence that we had a common ancestor somehow. One other alternative, you have to hold in mind, it is possible that there was an evolutionary process that games were experimented with and it was settled on this one other than by accident. Same thing, by the way, when it comes, of course, to physics. That's the better known case. That the things that are arbitrary in physics, like the certain constants and things like that, this has received a lot of attention, of course. There's the anthropic view that we happen to be in one of many, many universes in which the constants are well designed for us to be in it, and therefore to observe it. There's the other possibility, which I find much more enticing, but apparently hasn't led anywhere, that you want to define a structure which could evolve into the right constants. So the one that first attracted me early enough, I mean, it seems awfully arbitrary to me initially, that the dimension of the space we live in is 3. Now, what we mean by dimension has radically changed. So mathematicians want to say dimension in the small or in the large or something. This turns out to be dimension in the middle somewhere, right? So the perceptual dimension, I guess is what I want to say, is one possible way of saying it. You can argue easily enough that if the dimension weren't 3, then you wouldn't expect something like the inverse square law for a force. But if you're thinking of dimension as only integer valued, as not something that can vary continuously in some sense, then that sounds too arbitrary. So therefore have some nature of space in which you can have fractional dimensions, and of course the relevant notion is something called Hausdorff dimension, whatever that is. Yeah, it's essentially the relationship between the radius of a sphere and the amount of how much it contains. And that you would like some picture or some system in which you could argue that if it varied away from dimension 3, things would cause it to bounce back, to come back to dimension 3. That if you got over dimension 3, then the forces would dissipate too quickly, that sort of thing. And you would then maybe end up with a picture of space, of all of physics maybe, in which nothing was arbitrary. And in that case, I would say we would start thinking of it as a branch of mathematics. That hasn't happened yet. So we have to patch up the notion of arbitrary to make this work, and you can't escape the fact that you're going to end up deciding that things are interesting or not, and that's an important part of it. The importance of, by the way, of being interesting, if you want one hell of a lot of theorems, and you don't care, maybe I should say conclusions, and not care about the interest, then it's perfectly simple what you want to do. You want to adopt an inconsistent theory, and then you can prove everything, right? I mean, and it would have I mean, you'd have all the theorems you ever could, conclusions perhaps I should say, you'll ever need. So there's an interplay there, and so the whole thing may be a cheat, what I'm preaching. That's a possibility that I'm afraid does occur to me. I want shortly to open up to questions, because I think that'll be a lot more interesting than me keep expounding on these things. But I do want to mention, let me do that. I have a coda that can come later. So let me stop now. And nobody has objected yet to anything I've said. Let's object or do something. No questions? Yeah, Sultan.
You mentioned mathematics is not arbitrary. That's
Right.
a slick description, hard to object that. I'm now pressing you. Could you say, well, it's objective in some sense? So not arbitrary, but a little more like objective in some point like that.
So the question is, for the record, what's this have to do with objectivity? I haven't the slightest idea. What does that mean in this context?
That just means that now we can talk about mathematical truth and other things. Similarly, we talk about truth in experimental science.
Truth, as opposed to having necessary conclusions.
Exactly.
It strikes me as a separate question. You mean, I think you're asking what's the validity of logic or something?
Yeah, I mean, is there some kind of a, I don't know, let's say, continuum hypothesis somehow should be, this way about real numbers, should have a way which we would say is correct.
Okay, I'm going to have to, so the question again for the record is, do I have anything to say about, say, the truth of the continuum hypothesis? Right.
For example, that would be an application.
That would be a nice one.
Yeah.
So let me expound just a bit on that. I have, as Zoltan surely knows, a view about the foundations of mathematics that may not, I think, is becoming standard over time. So let me just talk about this just for a moment. By and large, the practice of mathematics was remarkably free of foundations. The semantics of the subject matter for most mathematicians was irrelevant. They had a semantics. They felt they knew what they were talking about when they were talking about the natural numbers, for instance. Albeit there were some areas that came up, particularly in analysis roughly 100 years ago, that seemed to be more complicated than that. When we came, and this turned out not to be mathematics, but when there arose a subject in which the semantics was not at all clear, namely computer science, set theory was found to be useless. And so we had to look entirely elsewhere for semantics, in which the continuum hypothesis appears to be totally irrelevant. Okay, so that's that first thing. Now, I was, as indicated in the introduction, in the business of building devices where you can vary. So I usually describe it as what happened to geometry in the 19th century happened to foundations in the 20th century. You took a much more expansive view. It wasn't a single foundations. There were many foundations. You would pick the one that you wanted to make interesting theorems, right? See, so watch what happened. I mean, look what happened in the 19th century for geometry. It started, I think it's fair to say, that it turns out you can find some earlier antecedents for this, but by and large, it was the case that in the year 1800, there was Euclidean. They didn't need the word Euclidean. There was geometry. It's what we now call Euclidean geometry. You didn't have to worry about alternatives. In the middle of the century, people found that explored alternative geometries. And by the end of the century, people no longer believed that the original one was describing this real world, which I think I pointed out actually is not a well-posed question until you say which physics you're going to use to decide whether it's describing it or not. But now let me point out that Kant was essentially right, albeit not when it came to the specific things about analyticity and synthetic and all that stuff. There was something special about Euclidean geometry. It was, in fact, it is, let me use the present tense, it is less arbitrary than the other geometries. I don't think you have to say it's innate. I think it is simply the fact that it's reasonably clear to me that this may be a peculiar, I may have trouble defending this, but that to say that space is positively curved or negatively curved, they both sound like arbitrary decisions, where to say it has no curvature at all sounds unarbitrary. I do know that as a very young kid, a friend and I measured the circumference of a tree and wondered what the diameter was and said, well, we took a little fruit juice glass and measured it there and saw it was about 3-to-1. And we're happy with that answer. It never occurred to either of us, and we had to be told years later that we could have been living in a space in which that ratio between diameter and circumference was dependent on scale, that it wasn't constant. I mean, so it was that sounded arbitrary, right? Whereas the neutral decision was to say that it's constant. And it seems to me there are a lot of things like that tell you that classical geometry was the least arbitrary. If you had to settle on one, that would be it. I don't think it has to do with, it's reasonably clear to me that if we lived in a space of non-zero curvature, we would build our blackboards to have zero curvature. We would need it to teach calculus. That's right. Right? I mean, that requires a zero curvature plane. So back to the continuum hypothesis. I don't think it's a well-posed question, as stated. I think there is a non-arbitrary notion of a minimal set theory, which allows things like the axioms of ZF, and I'm willing to bet anybody that will eventually be shown to satisfy the continuum hypothesis. That last I'm not sure of, but I'm reasonably would expect it, I think. I'd put odds on it, let's put it that way. But that you are making an arbitrary decision when you say, which set theory are you looking at? And so it is not an absolute question as posed, it seems to me, that the continuum hypothesis, you do need some other stuff you have to state to ask whether or not it's true. So these relationships in and out of the subject. So no, I'm not sure what I have to say about objectivity. I think you still will strive for non-arbitrariness. And in fact, it would appear that when you listen to the people in that business, as we had this conference on set theory last term, and in previous ones, people are looking for, if you look at it, are looking for non-arbitrary principles that would give you an answer. Because the continuum hypothesis as it is sounds too arbitrary. You have to say what it is you want your set theory to do before you're going to be able to answer the question. Yeah.
So can you count me as people that are skeptical about the arbitrary business?
I didn't use the word natural, I don't think. This real world is very arbitrary. So I guess I didn't say that. Perhaps I should have. When you talk about what's true in this particular world, that strikes me already as an arbitrary decision having been made. Right? I mean, that at the moment is the difference between physics, this clear difference between physics and mathematics is precisely that. Physics is about a particular world in which you can do experiments and things like that. I said it's possible that physics will develop to a point where all the peculiarities of this real world, well, maybe not all, but a huge amount of them, can be explained away as arbitrary, non-arbitrary. So yes, somebody better get a better hold of what is meant by arbitrary. So this is work in process, as it were, in whatever the right word is there. The fact that the ordinary human brain has certain funny ways of doing it strikes me as an arbitrary fact about the nature of human brains, and not more than that. So it doesn't bother me terribly. In fact, I mean, one can make a very good argument that most of the history of science is to refute common sense, right? I mean, but in doing so, you're trying to go by the folklore aspect of it. That's arbitrary. Whereas when it reaches by trying to use it based on some sort of experimental evidence, I think you're reaching there for less arbitrariness. But again, that's not mathematics. If you want to allow the possibility that there's another intelligent species somewhere that conclude, their number theory will have different, some of their theorems in number theory will contradict our theorems in number theory, then I don't know what I could say to you. I mean, that is a possibility, I suppose. But I wouldn't consider it a realistic one. So that's not, I'm saying why I'm not answering the question, right? Yeah.
I have a slightly different question, also about arbitrariness. So you started off saying mathematics is one way of thinking about mathematics as being non-arbitrary. So let's grant then you said it's sort of continuum of cases with things like chess and Go.
Right.
So I guess the question now is, raised in my mind, is the boundary around mathematics, how arbitrary counts as mathematics? Is that arbitrary?
Well, as I said,
Where do we start with the game?
no, there's problems. If you forget about the necessity for theorems, then I pointed out you could go all the way to non-arbitrary and have no theorems, all the way to non-arbitrary. And then if you forget about the interest involved, you can do the same thing. Let me go back to chess and Go and whatnot. If you proved, this isn't precisely an answer to your question, though. If somebody proved that, say, there was a strategy to win in chess for the first player, for white, and the fact that you could prove that existence doesn't mean that you could actually get hold of it, right? I mean, there are games that you can prove there's a strategy for one player or the other, and yet you have no idea what the strategy is. I don't think that would be considered a mathematical result. I don't think it would be considered a result in mathematics, in fact, in ordinary usage. Same with Go, unless you remove the 19. If you had a theorem about Go which was for an arbitrary shape, well, I just said shape there, let's start with a square board, but of arbitrary size, it would begin to sound more like mathematics, still not mathematics. If you then had a theorem about Go played on an arbitrary graph on a plane, and if you have the necessary and sufficient conditions, a nice statement of the necessary and sufficient conditions for that graph to determine who has a strategy, that I think would be accepted as a mathematical result in mathematics. So,
Would we expect if we went to the extraterrestrials that they would make probably the division in the same place?
yeah, I would. Is there a hand? No, there wasn't. So again, I'm not sure if I'm answering your questions, but as I said, this is work in progress or process, whichever word is relevant there. Is that a hand? Do I have to answer a question? Ask a question? Yeah, Murray.
Maybe I'm mishearing you, but you seem to be saying to some extent mathematics is defined by the questions you ask.
I just said it was the theorems you end up with. Oh, okay, so, yes, I certainly am. I think that's unavoidable, right? I mean, I don't know a human endeavor which isn't, intellectual endeavor which isn't so defined. By the way, for the record, is mathematics defined by the questions that are asked? Yeah, of course.
It goes a little bit farther than that. A very famous French mathematician, so famous I forgot his name, said, il y a des questions qui se posent et qui vont se pose. There are the questions that pose themselves and that one poses to oneself. I don't know how you draw the distinction, but we all feel intuitively that there's something in there.
Yeah, the questions that pose themselves are the non-arbitrary ones. That's what makes them, that's how you know that they're posed, that they answer, they pose themselves. It's because of their very non-arbitrariness. The questions we end up asking for practice, the finger exercises, those are arbitrary until we get to the really good questions.
Challenge you about the proof that there's a strategy for the first player in chess. In theory, you could enumerate all possible games of chess.
In theory.
In theory, and determine it. But I still think it would be a nice theorem to prove without enumeration.
Well, of course, I wouldn't, in fact, well, okay, now, see, there's another huge problem, which I thought I would try to subsume by that notion of interest, maybe. You know, everything in mathematics is a tautology. And that's not, of course, at all what we mean. That's a different subject. There is a huge difference between arbitrary tautologies and the things that we call, maybe in theory, all the theorems are tautologies. But not all tautologies are theorems, right? I mean, so yes, I mean, so let's take the example people usually point to, and that's the game invented among others by John Nash. In fact, by the way, just since we're on the subject, there is a scene in the movie where they don't say they're playing Go. You're supposed to assume they're playing Go. And Nash, the young Nash, as a student at Princeton, is upset because the first player should win. Now, it's what's clear at the Go board is it has far too many stones on it, so it can't be Go, because serious Go players would never still be playing with that many stones left on the board. So I thought, oh, that Nash must have, when Nash invented his game, which I won't try to describe here, he did play it on a Go board, and he supplied the proof using some algebraic topology that there had to be a strategy for the first player. I actually got hold of the scriptwriters on that one, and I was wrong. They said they put that many stones on the Go board because it looked nicer. And they said, but in fact, they did film some other scenes in which Nash goes and invents the game of Nash. I was wrong in my inference on it. Let me describe a game that's simpler to describe. In fact, you've all played it. Its Japanese name is Gomoku, and it's a wonderful pun there. The word Go is the Japanese word for 5. It is also the word for small stones. And in the first case, it describes the standard game of Go. This is a different game, played with the same stones on the same board, right? And it's 5 in a row. You've all played it by every culture, I think, gets around to inventing that game. You play on a rectilinear grid. You don't have to specify the size. Take it to be unbounded size, and first player who gets 5 in a row of his color wins. This is one in which it's easy to prove, chances are probably there's a strategy for both sides to draw. So let me be careful how I state this. It's easy to prove that there is no strategy for the second player to win, because you have a little construction, you take any possible strategy for the second player to win, and you can quickly convert it into one for the first player to win. So therefore, there couldn't have been one for the second player to win. If you could supply the fact that the game must terminate, then you would have a strategy for the first player. The game of Nash has that nice feature. Again, because of a little algebraic topology, you know that there has to be a winner if they play long enough. And that's where the algebraic topology comes in. Notice there's nothing like an enumeration here, and therefore these are mildly interesting theorems. If they were obtained by enumeration, they wouldn't be interesting theorems. So part of the word interest there has to do with the proof, the nature of the proof. And let me, since, I mean, there should be someday a philosophy of the aesthetics of mathematics. Most people, when asked, what's the word of aesthetics that mathematicians are most apt to use, say, well, the word is clearly elegant. Well, not true if you think about it. The word is interesting. You're using it so often you don't even notice it as an aesthetic judgment. And there are all sorts of theorems that are very interesting which are totally inelegant, because they have nice, the interest will tend to come from the fact that they have a lot of nice corollaries and they tell you about a lot. And then there are a few things, like the theorem I just described, without going into the details, in which the interest is very limited, but it has a nice, elegant little proof comes out. I mean, Nash, as a student came up with. By and large, if a speaker in mathematics starts with the fact that the theorem I'm going to prove isn't all that interesting, but the proof is interesting, you know that you might find an excuse to get out of the room, right? I mean, this is usually a cop-out for not having an interesting theorem. But this is a good part of it. So the complication coming in from this notion of interest is going to be a devious complication. It can rest on the nature of the proof. There are things that theorems that mathematicians in particular like to tell each other, and the theorems are uninteresting, but they have wonderful little proofs. And so this is a part of it, and as I say, it's one that I can only say, well, maybe this isn't even philosophical anymore. Maybe aesthetic judgments themselves, the actual judgments, aren't part of philosophy. Yeah?
How can mathematics be non-arbitrary when it's done by humans living in an arbitrary world?
Not easy. Take some work. That's okay, right? I mean, but you're quite right. It may not be anywhere near as arbitrary as we think, but you certainly in hell can strive for it. That's clear. So yes, if you want to, I would be willing to modify or put this in as a caveat. That quite possibly is all terribly arbitrary, but what you're trying to be as unarbitrary as possible. I don't, well, if I'm prepared to say that is the same as non-arbitrary. Now, that's not what Platonists meant. Okay, so now I don't think I need Platonism there. The fact that mathematicians often become Platonists it's the same phenomenon that a playwright, let's say, let me say scriptwriter rather than playwright, he often finds that the dialogue is writing itself, particularly if you're doing soap operas and things like that, right? I mean, he's sitting there and the dialogue's writing itself. They never fall into the trap of thinking, therefore, the characters exist. Mathematicians do. That's what, leave me, I do have a coda, as it were, so let me just before let's stop the questioning a little bit before, it's 20 of 6 already. Yeah, there was a hand up there? Well, first of all, no, you can't. I mean, nobody's got a good theorem proving program. There are profound problems there. They're usually best understood to be, or summarized by the phrase problem of equality. Mathematicians are constantly saying this is the same as that when you don't, it's very nebulous what they're saying at that point. There are two uses of the word proof. When I say I can prove, or let's be more accurate, Tarski proved that there is a proof that, we have to be careful here, Tarski didn't prove it. A corollary of what Tarski proved proves that there aren't any 16-dimensional division algebras, associative or not, over the algebraic reals. Why? Because Tarski proved that that's a decidable theory, and the decisions only depend upon the definition of real closed field, and it was proven for the real field using a lot of topology. That's right. So, which wouldn't apply at all to the algebraic reals. Okay, so the inner proof is a technical notion. You find out, you notice that this is a first order statement and all that. The outer thing, Tarski proved, that's the real notion, the public notion, the one you're usually using, and we're nowhere near that. I have this peculiar assertion that proof, those proofs, the ones that live in real life, exist in fact only in their performance, and what's written is a score thereof. And that's why, well, that's a whole nother lecture. But that's a very informal notion. So in fact, the proofs we actually use to convince each other that proofs may exist. Yes, I would like to see a program doing something. I would like to see a machine develop a personality. I would like to see persons residing in machines. I think they're of the same, they'll happen about the same time. I would guess that we'll have machines that can make us similar aesthetic judgments about theorems as humans, that when we have theorems that we recognize as persons, when we have machines that we recognize as persons. One more hand, then I've got my coda, yeah. You've anticipated my coda. I will not repeat the question for the record because it will sound like it's a total. Okay, so the coda is the following. There was a name missing from that list that I started with. There was a philosopher, professor of philosophy at Brown University named John Ladd. Over the years, I've met a remarkable number of people who were strongly influenced by John Ladd in all sorts of subjects, by the way. I never took a course from him, never really sat at his feet, but I was one of many that he had something of a good influence on. I think the second week I was at Brown, he sat down next to me. He was chief resident fellow, and he considered it part of his job to eat lunch with the students in the big dining room we all ate lunch in those days. And so he sat down next to me. Now, I began by talking about we have to find ways to explain to other people what it is that mathematicians do. Philosophers have to do the same thing, of course. There's a huge difference between the public view of, well, I did an inadvertent experiment years ago, which I've repeated a number of times. Say to, the first time it was with some high school students, and I was casually mentioned a philosopher I knew. I said a professional philosopher, and that phrase got a rise, professional philosopher. How could there be such things, right? I mean, they were aware of some great philosophers, but that same sort of thing. And I think, so let's see, by the time I was a freshman, I think I had some awareness that professors of philosophy wrote papers. And as far as I could tell, though, all they did was refute other philosophers. And so I said that. What I said to him was, what's it like being a member of a profession in which your reputation rests on your ability to refute others? And he proceeded to tell me about synthesis, antithesis, thesis, antithesis, and synthesis, taking as his main example Thomas, synthesizing essentially the Greek thought and the Christian thought. Well, that's just the beginning of the story. Some weeks later, but again, it was my first semester at Brown, also at lunch, but a more formal occasion, I find myself sitting next to someone. Now, I don't know who it was. I didn't know who it was even the next day. I don't think I ever saw him again. I'm assuming he was a philosopher. To make conversation with me, he said, what do you think about logicism and formalism and intuitionism? And I said, oh, I think they should be synthesized. And he immediately got a different expression on his face. He actually started, maybe I should listen to this person sort of expression. And he said, that's very interesting. And there was a quietness. I mean, I was supposed to say something. And so I didn't know really what the words meant. I think I had heard the words, and I had some very vague idea about what they referred to. But I did know that in the 19th century, they had learned to model these different kinds of geometry in each other. So I said, surely we will learn to reduce each of them to any of the other two, right? I mean, So any question in one can be translated into a question in the other. Yeah, I mean, it turns out that to make that process easy turned out to be a good hunk of the research of Andrei Shedroff and me, just to do that sort of thing. But I didn't know that then. But then I did say, and I only recently remembered all this again. I mean, I've been remembering it over and over the years. I said, of course, when you translate a question from one place to the other, it can look quite different. And in fact, if you didn't know what the original question is, it wouldn't look interesting. And so I said, but of course, that shows you that the real issue is what do you find interesting? I'd forgotten temporarily this, Freyd. So in other words, I've just come back to where I was at the age of, the first freshman year, which also, of course, might mean that I didn't come back to it. It was always there, and this biased my whole approach, right? But I'm prepared, at least for the near future, to continue to defend the principle that finally what we really have to do is state what do we find interesting and why. And that should be the rest of the subject of mathematics. I guess that's the end. Good. Dinner time.